talking about the overconvergent Eichler-Shimura map.
Thank you very much. I would really like to thank the organizers for giving me and Vincent the chance to give these two talks who are related. So I'm going to continue, in a certain sense, to discuss about things he outlined in his talk. So let me fix some notation. So I would like to just suppose that p is larger or equal to 5 is a prime integer, and n is larger or equal than 3. P does not divide n. So I'd like to fix k finite extension of QP, which I'm going to suppose large, and we'll see how large we need to have it. And let us fix k bar an algebraic closure of k, and gk the Galois group of k bar over k. So let's fix kappa, as in Vincent's talk, a weight. So I'm going to take a k rational weight. So let's recall that this is just a continuous homomorphism, group homomorphism, from zp star to kp star. And let's recall, as Vincent pointed out, that the integers are considered to be a subset of a subgroup of this one by sending an integer k to the character sending t in zp star to t to the k. So then I would like to remind you of a construction of an object called overconvergent modular symbols of weight k, or weight kappa that we fixed. So this is a construction that Glenn Stevens has made and used in many ways. So let's just fix T0 Zp star cross Zp. So it's a compact subset of Zp squared. It's not a group. It has an action of the Iwahori subgroup of GL2 Zp. So these are matrices A, B, C, D in GL2 Zp with the property that P divides C. And it has also an action of Zp star, just multiplying diagonally. And let me denote by A kappa the set of functions from T0 to K, which are analytic. So they are globally analytic, and they are homogeneous of weight kappa for the action of Zp star. In other words, f of Tx is kappa of t times f of x for t in Zp star and x in T0. So this is a large infinity-dimensional k vector space, and it has an action by this Iwahori group. And we denote by d kappa the continuous dual continuous k-linear homomorphism from A kappa to kappa. This also inherits the dual action of the Iwahori subgroup, and we will be interested in especially in the group which I'm going to denote gamma, which is gamma 1 of n intersect gamma 0 of p. So this space Glenn calls analytic distributions on T0 of weight kappa. And then the object that we'd like to look at is H1 group cohomology for this group, this arithmetic group gamma, which is the intersection of gamma 1 of n and gamma 0 p, with values in these analytic distributions. So let's call this sort of overconvergent modular symbols of weight kappa. So this space has a natural action of Hecke operators TL for L not dividing NP and of UP. The UP operator acts completely continuously. And moreover, okay, so one of the things Glenn has done with this object was to construct p-adic L functions attached to modular forms for the group gamma. But there is something else about this. So one can think about this group, in fact, can be identified with the étale cohomology on y of np. So y of np is the affine modular curve with this level corresponding to this group. And I would like to think about, I mean, this is a curve over Q. I'm going to base change over K bar, and we can think about cohomology with coefficients in this large module. And as such, this has Galois action, an action of the Galois group of K bar over K. So what we have is we have this object, which is an infinite dimensional K vector space with an action of GK. So it's a sort of unusual p-adic Galois representation, and it has an action. It's a Hecke module. And one of the goals of my talk today, so I'd like to discuss this Galois representation as a GK representation from a p-adic Hodge theoretic point of view. And let me just talk today about the Hodge state structure of this Galois representation. Okay, so this is the goal. And here is the outline of what we can do so far. W rational number. Say W is between, let me make it a W, small w, between, is smaller than P over P plus 1. So this is somehow the bottom range of Vincent's So I'm going to recall the strict neighborhoods of the strict neighborhood of the ordinary locus in the modular curve that Vincent discussed about. So let me consider, I would like to consider two modular curves, in fact. One is x1 of n, and let's base change it over k. And there is another one, which is x of np. So x1 of n classifies generalized elliptic curves with gamma 1 of n level structure. And this one will classify generalized elliptic curves with gamma 1 of n and gamma 0 p level structure. Okay, so inside here, we'll consider x1 of n w, which Vincent looked at. So this is the points x in x1 of n, which we think as a rigid analytic space over k. And so Vincent looked at this Hodge state map and this this index. I'll do something maybe it's equivalent. I'd like to look at the Eisenstein series of weight p minus 1, level 1, evaluate it at this point, look at the p-adic absolute value, and I'm going to take all the points for which this absolute value is larger or equal than p to the minus w. So this is equivalent to what Vincent was doing, because I remind you that EP minus 1 is a lift to characteristic 0 of the Hasse invariant. Okay, so this is an affinoid defined over K. So it's a very sort of very far away from being proper. It's a very open sort of rigid subspace of x1 of n. So now for certain reasons, I would like to work with this curve instead of this one, although this one is the good one. There is a section, so the natural projection, which is forgetting the order P subgroup, has a natural section, namely a section which sends a point which is an elliptic curve and a level n structure to, I have to add a subgroup of order P, and by the range where I took W, every elliptic curve here has a canonical subgroup. So I add that canonical subgroup, I have and I obtain a point in x of np. So this is a section of the projection, and therefore the image of this section, I'll denote it x and p of w, and it is isomorphic to x1 of nw. Okay, so we have this picture. So now so let omega kappa be, let me put a k here to understand that this is the generic fiber of the sheaf, of the integral sheaf that Vincent talked about. So this is it's an invertible sheaf on X and PW. So Vincent defined it here, but these are isomorphic, such that its global sections these are overconvergent modular forms of weight kappa, and let me put a W there, overconvergent with W measure of overconvergence. Vincent actually took a direct limit, so he took all such things. I will fix a W and just work with the sections of this sheaf over W. There should be a W here also, but okay. So then, sorry? Yeah, you're right. So in fact, I would need such W's only work for special kappas. You're right. I would need to take. So let me then do the following. So let me take kappa of the following form. So let tau denote the Teichmüller character. Let's suppose S is an element in OK, and let's take kappa weight of the following type. Kappa of T is tau of the reduction to the I times the diamond bracket of T to the S, where I is some integer between 0 and p minus 2. So anyway, these are a large family of weights. For these weights, any W will work. And in particular, the integers are of this type. So now, what can we do? So the first thing that we can do is we can define a Galois equivariant and the Hecke equivariant map, which goes from overconvergent modular symbols of weight kappa, tensor over K with the CP, to these overconvergent modular forms. Kappa plus 2 tensor over K with CP as well.
You don't need to complete it all.
Where?
You don't need to complete with the tensor products at all, it's just tensor CP.
You're right, I need to complete it. Yeah. And I need to complete this one too. Okay, so it's complicated to, we are not able to analyze this map in all the situations, but we are able to do it in a certain particular case. Namely, in the situation, if kappa is K, is an integer, larger or equal to 0, and if we fix a slope h, we can prove that in fact this map from overconvergent modular symbols to overconvergent modular forms, where I take slope smaller equal to h, k plus 2, slope smaller equal to h, that this map, yeah, k plus 2, no, k is kappa. K is kappa. No, so we need, here's k, and here's k plus 2. So this is surjective.
Are these spaces of finite dimension?
Now they are finite dimensional, yes. So now you don't need to complete, you are saying. Yeah. Okay, so now, this, I mean, okay, so we can show that this is surjective. This is actually has an interesting consequence, namely, exactly in this situation where k is an integer and k is larger or equal to 0, there is a map from dk to vk. Vk is the symmetric power on k square as a representation of the Wahori or of gamma. This induces a map on the level of cohomology groups, and this can be seen as classical modular symbols. As such, they have an action of the Hecke operators. We can take we can take the slope smaller or equal to h part for the action of the UP operator on both of them, and it turns out that this is an isomorphism. In fact, this theorem of Glenn Stevens, which has been generalized to basically all the situations where such objects appear by Eric Urbain and other people, is actually not that hard. Okay, so let me try to see what we have. So we have our map, surjective to
H is again smaller, right? H is
H?
still small throughout.
It's that h over there. This h, yeah. H small. If h is not small, this is not true. This, we said, is isomorphic to classical modular symbol, classical modular symbols slope small equal to h. And by classical Eichler-Shimura, there is a surjective projection map from this to sections to classical modular forms of weight k plus 2. And we can take slope smaller equal to h. Obviously, we have a restriction. So this is the whole modular curve. We restrict to this aphenoid. This is an injective map. But because this is an isomorphism and we have two surjective maps, this is surjective. And therefore, we get an isomorphism which says that overconvergent modular forms of integer weight and small slope are classical. So we get a different proof of the classicality result. So we think that, in fact, this should work for Hilbert modular forms, but we have not yet checked these details. In any case, there is this possibility. So in what follows, I would like to, okay, so I somehow outlined two things, namely an Eichler-Shimura map, if you would like to call it like this with me, going to overconvergent modular forms of weight kappa plus 2. So this for any kappa of that form. There is a map like this, and 2, the surjectivity in the case kappas in Z larger or equal to 0, and the slope is smaller than kappa plus 1, this map is surjective. So I'd like to talk a little bit and explain how this map is defined, and then how we analyze it in this relatively simple situation. Okay, so if you think about it, this is somehow a Tal cohomology on the whole modular curve, on the global modular curve. We tensor it with a CPE, which we'd like to think as being sort of the simplest Fontaine ring, or ring of p-adic periods. And we want a map to this object. This sheaf is sort of made out of differentials. So anyway, if one wants, this is something like a comparison map. So in order to define it, we'll do the following. We'll do a comparison map. The difficulty to dealing with this comparison map, again, is that this is, we have sheaves on a very small aphenoid in the modular curve. And here we deal with cohomology on the global curve. So there is some restriction that sort of is very difficult to control. Anyway, let me point out what we want to do. So we have x1 of n w isomorphic to x of n p w. So this is contained in x1 of n. This is contained in x of np, and we have this projection. So then I would like to recall that there is a formal model for this aphenoid. So this is formal completion. So let's say p-adic completion of the block. Okay, so what do we do? Of the open consisting of the complement of infinity in the exceptional divisor of the blow-up So there is a model of x1 of n over OK. It's a smooth model. And we blow this up at the ideal generated by PW and EP minus 1 evaluated at the universal elliptic curve and some generator of the differentials. So this is some formal scheme whose generic fiber is exactly x1 of n w, which we said is the same as xn pw. So we can think about this as a formal model for this as well. And one can put log structures on this given by sort of the singularities and the cusps, such that this becomes log smooth. And we endow this rigid space with the log structure coming from the cusps. And to this pair, so we denote by x sort of Faltings' site associated to this pair. If you don't mind, I would like to denote this by x, so it will be different from Vincent's talk, where he defined by this the formal scheme. So what is it? So let me recall. So to define a site, one needs to first define a category. So the category of open sets. Let's denote it by E XX. So the objects are pairs U, W, where U and W are, U is the log formal scheme and W is the log rigid space. U comes with a morphism to X, which is et al. In fact, it is Kummer log et al. And W comes with a map to UK bar, which is finite, and et al. So again, this is finite and Kummer log et al.
So you say again, where's the log structure on X in the formal scheme?
So
Structures on the kind of normal crossings in the special fiber, or the log structure is
so there is a, I mean, this log structure is not that, I mean, locally X around the singular points looks like this. Because of the W. So if A is 1, you can think about the special fiber as a divisor and take the log structure associated to that. If A is larger than 1, then one has to do something else. And
But you also said there was you put some log structure at the cusps.
at the cusp as well, yes. Right. So then the morphism in this category. So if you have UW and U prime W prime, a morphism is a pair FG, where F is a map from U to U prime defined over X, and G is a morphism from W to W prime, such that the following diagram commutes. And then one has to define coverings in order to make a site. So these are so to define the coverings, let's consider a family of maps. So we'll say that this family is of type alpha. If ui to u is a covering in the Kummer-Log et al. Topology of U, and Wi is isomorphic to W crossover U with Ui, and for all I. And we'll say that it is of type beta if all the UIs are isomorphic, so there is some U such that UI isomorphic to U for all I, and the family Wi to W is a covering. And we declare the families of these two types coverings, and we take the topology generated by them. So in other words, a covering is a composition of a finite number of such families of type alpha or beta. So then we obtain a site, and this site there are two interesting functors. So one of them, so this is finite Kummer-Log et al. On xk bar. X is the affinoid in the modular curve, and there is a functor sending uw to w, and there is one from the Kummer-Log et al. Site on the formal scheme sending a u to uk bar. So call this v, and we call this u. So we are going to use these two functors. On the one hand, we can use the inverse image of with respect to v. For example, if for the sheaves omega k, which are sheaves they are coherent on the formal scheme, and we can think of them as sheaves on X. So in other words, we'll take V upper star of omega k. So this is a sheave on X, and it is an V upper star of OX module. Moreover, every time we'll have, for example, locally constant sheaves or projective systems or projective limits of locally constant sheaves on X, we can think of them as being sheaves on Faltings' site by using U law star. So in particular, let's look at this d kappa. So d kappa can be seen as a, okay, so just as an object, as a representation of gamma. This is a Banach module. It is a Banach module over analytic distributions on ZP star, in fact. But it is a Banach module. It has a norm, and therefore I can look at the unit ball inside. So all the distributions with the property that the norm is small or equal to 1. And I would like to think about the projective system of torsion representations. They are not finite, but they are torsion of gamma. And I can think of these as sort of sheaves on the Kummer-Log et al. Site of the whole curve where the log structure is at the cusp. And I can restrict them to the affinoid. So in particular, let me look at this. So this is a continuous sheaf on Faltings' site. So therefore, we can see all the sheaves that we have as sheaves on Faltings' site. And there is a new one which will help us do the Hodge-Tate comparison, namely, let me recall one that is sort of.
So decay node is kind of a pure system of sheaves?
Say it again?
You think of decay node as a kind of pure system?
Yes, projective system. Projective system of torsion sheaves. This is what I call a continuous sheaf will always be a projective system of torsion sheaves. So this is the Uwe Janssen stuff about. So the main sheaf, so say the structure sheaf of this site, let's call it OX. So it's defined in the following way. So it's sections over a pair UW. So this is just the normalization of the global sections of U in the global sections of W. So this is a priori, initially it's a pre-sheaf, and then one can prove that it is a sheaf. And I would like to think about the continuous sheaf, which has as components OX divided by P to the n OX. So this is the sheaf that allows us to compare état local systems with the RAM sheaves on proper schemes. So we are far away from having a proper scheme, and therefore, okay. So here is what we are going to do. So let me denote by d kappa x. So this is going to be a sheaf on X, and it's going to be the continuous sheaf d kappa 0 divided by P to the n d kappa 0 tensor over OK with OX divided by P to the n OX. So this is a sheaf on it's a sheaf on X. And I will define another one. Let's call omega kappa, and I'll put an X under it. So I'll take the inverse image of omega kappa, and I will take a tensor with the inverse image of OX with this. So I have to define again a continuous sheaf. So I basically tensor the sheaves that I'm interested in comparing, dk and omega, d kappa and omega kappa. I tensor them with OX, but I did it in this sort of continuous way, let's say. So now
Little omega kf is like just kind of pulling back a coherent sheaf from one thing to another, and the top one is like extending the scalars from a locally constant sheaf to
right, but I'm tensoring with this OX. It's like you're tensoring with CP if you have a representation. Okay, so now I have two sheaves on X, and so let me see if I have arrived to, yes. So the theorem that I would like to prove is the following. So first, there is a natural GK equivariant map from H1. So this is cohomology on Faltings' site with values in dkx. For some reason, I would like, if you don't mind, to twist here. This is a Tate twist by 1. And I'm going to invert P. We can invert P outside if this makes 2H0 on X omega kappa plus 2X with P inverted. And this is nothing else but what we had before. This is X, which maybe I should, it's NPW, omega kappa plus 2. And then I have to tensor with CP. So we have a natural equivariant map like this. The second point, so I'm claiming both terms, I mean, have actions of Hecke operators, TL for L not dividing NP and UP, such that if H is any finite slope, so the map, so I should have said is part of the theorem that this group has a slope a slope decomposition, which is not at all obvious, but the map to overconvergent modular forms is an isomorphism.
So when you let's move to H, it's implicit that you inverted P.
Yes, I'm sorry. You're right. I have to invert P here. Yes. So this is the theorem, and this allows us to get the first map. And I'll say in a second, in fact, how this works. Sorry? No. In fact, it works for any kappa, but then I have to restrict the W. This is true for any kappa and for any finite slope. So this is really an isomorphism. So now, how does this help us get that map? So we have H1 gamma d kappa tensor CP. There is a map from this. We can map it to, I don't know how to call this. So just thinking of this as a sheaf on the Faltings' site. And by yeah, it's the U star. Okay. And then, of course, there is a natural map from this to H1. Yeah, I do. You're right. Here I don't need to tensor with CP anymore because it's here, but I need to invert P. And finally, and this is with coefficients in omega kappa plus 2. And this part is an isomorphism if we take the finite slope part. And this is in general a restriction. So you compute cohomology on the whole modular curve to something which is much smaller, and in general is difficult to control. So this is how one obtains the composition of this. Is then the map 1. So let me say how one obtains the first theorem, this theorem. So on the proof of the theorem. So what happens is that in general d kappa, I mean if k is an integer, a positive integer, we saw that there is a map to vk and its kernel sort of provides a sort of a filtration of dk, but in general if kappa is not an integer, dk doesn't have a filtration. So in a certain sense, okay, so dk in general is difficult to analyze, but I claim that dkx in fact has a nice filtration, decreasing filtration. So d kappa x is field -1, and then it contains field 0, and then field 1, and so on. And the properties of this filtration are, first of all, that we can compute the graded pieces, namely field m divided by field m plus 1. So this isomorphic has continuous sheaves on x with omega x kappa minus 2m minus 2 twisted by m plus 1 for all m larger equal than -1. So in other words, the graded pieces of this filtration, they are expressed in terms of overconvergent sheaves of moreover, one can even compute so let me write, let's say, a lemma. So we can compute the cohomology of these quotients. So dkx divided by the mth filtration, and we obtain, actually for h0 we obtain something really integral, omega kappa minus 2m plus 4 So this actually can be computed integrally. For h1 though, one has to invert p. So I said we have to invert P, and I didn't write it. Sorry. So what happens? So you see that here it depends. The result, the sections here depend on M. So when M varies, in fact, one can pass to the projective limits and prove that H0x of dkx is in fact 0, because the maps between these give 0 in the limit. Here, for H1, there's something very interesting happens. You see that the result is independent of M, of the filtration. So one sort of has the feeling that one can pass to the projective limit and deduce that H1x dkx is actually this. But this is not true, because this would have been true if I didn't have to invert P. But as it is, this doesn't work. And then anyway, Hix dkx, these are 0 for all I larger or equal to 2. And now to prove the theorem, what one has to do is fix an H and choose an integer j larger than h. And then we have an exact sequence of sheaves on Faltings' site. And let me just write the relevant part of the long exact cohomology sequence. So these are modular, overconvergent modular forms. I have to invert P all the time, even here. So then these are overconvergent modular forms. This module has a slope decomposition. And by an explicit computation, one can show that the eigenvalues of UP on H1 with values in the jth filtration are actually, the valuation of the eigenvalues are larger or equal to j plus 1. So then a relatively simple lemma about on functional analysis shows that this module, whose topological structure we don't understand very well, position, and this one on this one the slopes are large. This one has a slope smaller equal to h decomposition, and the slope smaller equal to h of this module is isomorphic to the slope smaller equal to h of this one. Okay, so I guess I'm going to stop here.